Oh no, I'm on now. Hey people.
Party people.
Abby. How are you? All right, let's see. Where is everybody? Here we go. Hey Bailey, Alex. We're keeping Ethan awake. Excellent. All right, I'm gonna give everybody just a second to file in.
No, leave it.
Looks like we got most of you. How are y'all doing? Nobody answers. You just stare at me. Okay.
I did have one question on the lab.
Ma'am.
Sorry. For the third conclusion question, we couldn't figure out what it was talking about when it was saying analysis items 1 and 2.
Okay. All right, so conclusion question. Let me look at it real quick. I'm gonna pull it all up because I'm gonna go through it a little bit with you guys before we get done. Okay. Yeah, I'm gonna go through some of it with you guys. And then did you get to watch the whole video already? Okay, good. All right. So if it wasn't in the video, I'm probably not worrying about it. But let me look at what it said. Third conclusion question. Oh, the one that says, oh, maybe yours looks, no, wait a minute. What does it say, Abby? How does it read?
Using the graph shown at the beginning of this lab, determine the minimum mass of water necessary. Kind of from there.
Yeah, I think so.
There was a question similar in the final, in the last, like where it was showing questions. There was a similar question, but it wasn't the same.
Yeah, just do the ones that we did in the video.
Okay.
And I'll look back at that because I'm looking at my copy. Sometimes I think my copy is slightly different from yours. They can do that if it's off by like a year or 2 years in publication. Sometimes there's a difference. And I may have, trying to figure out where I got you, if I got your lab. I got your lab out of it's a PDF. So I didn't take it out of my book. It's a PDF of the book. So there may be a difference. So I'll look at that because I don't even have a third conclusion question here. So it must be in the PDF. All right, so I'll look it up. They're supposed to be the same, but occasionally we find stuff like that where you look at it and you're like, that's not the same thing. All right. Did anybody else have a question before we start, or?
We had one more question.
One more? Okay, go for it, Abby.
On the first one where it says, why was it important to keep the amount of cold water used to wash the KNO3 as small as possible? We found where it mentioned that, where it said you need to use a small amount, but I didn't find why.
Okay, we're gonna look through it real quick, and I'll make sure that we've covered everything when we get to the lab. Let's do our lesson first, though, if that's cool, and then we'll kind of look over that lab with everybody. All right, so I think we've got everybody here, at least everybody here that's coming. And so let's go ahead and just look over this week's lesson, okay? All right. So you had some pre-reading questions at the beginning of your chapter that talked about just kind of getting you ready for the concepts that were being covered here. So one of them was, when ice melts, what happens to its chemical composition? Does anybody want to offer up an answer for that one? When ice melts, what happens to its chemical composition?
The chemical composition stays the same, the state
right.
changes.
Got it. So yeah, its physical state's going to change, but its chemical composition is not going to change because this was a melting ice is a physical, not a chemical change. All right, and then it also asked, name a source of energy for your body. Anybody? You can type it in the chat box if you don't want to answer. Nobody wants, there we go, there we go. Oh, nope. Food, Michael says food. Okay, that's a good one. There you go, food. So yes, we're gonna require food, and we're also gonna require oxygen to create the chemical reaction in our body that's aerobic respiration. And that's how we function, which is, as some of you guys know, exactly opposite that of, oh, Cole's saying he's not let in. Dude, I have everybody let in. So, okay. Anyway, it's exactly opposite. There they are. Exactly opposite photosynthesis. So, all right. Name some temperature scales. There's probably 3 you're most familiar with.
Fahrenheit,
Fahrenheit, there's 1.
Celsius,
Yep, and Kelvin's down here in the box from Abby. Yep. Fahrenheit, Celsius, and Kelvin. Do we use Kelvin often?
no.
Okay. What's the difference? What's the big thing about Kelvin to remember?
It's 0 is absolute 0.
Right, Alex. What's that mean?
It's the coldest it can get.
Right. What happens at absolute 0?
There is no movement.
Right. No movement of particles. So it's really a very theoretical concept there. All right. And then why don't you tell me what's the difference between a physical property and a chemical property? Who can go there for me? Yeah, how about a physical property? Who wants to give me a definition for a physical property? Anybody? Do, 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 do. It's like Jeopardy here, y'all. All right, so how about examples of physical properties? I know you can do that because it was in your homework. I've admitted him twice now. I don't know why he wouldn't come in. So physical properties are things, there we go. So physical property, color. Also say things like, electrical conductivity, hardness, whether or not something has luster or is reflective, right? And how about some chemical properties? Anybody want to give some examples of chemical properties? You can do it. I know you can do it. Nobody. Hold on, I'm pulling up your thing and opening it up for you. Let's see. All right, so chemical properties, things like whether or not a substance is reactive, that's a chemical property. That's probably going to be our biggest one that we're going to deal with, right? Especially in this class. All right, so why don't I share, yeah, how it reacts under certain temperatures. There you go. Abby's adding stuff. Excellent. All right. Y'all, my juniors were like a gazillion times chit-chattier than you are. I know you guys can talk because I've heard you. So let's do, whoops. I've got too many buttons going down here. Let's go ahead and I'm going to share my screen of your notes. And what we're going to do is we're going to go over some of what this chapter covered for the sake of making sure we have a good understanding of it all. And then I'm going to go over with you guys some of the lab because I want to make sure you guys are comfortable because it's a longer and more complicated lab. All right, so I asked you guys to give me some of these review answers, and that will give you that. Yeah, I can't even speak today, y'all. That should cover at least this first section here, and some of the questions that we've already asked, some of the questions that were on your homework, and some that are different. So how about the first one? So what's energy? We talked about types of energy in your homework. Can somebody define energy for me? Yes, Jack.
Energy is the capacity to do work.
That's right, capacity to do work. So when we did physical science last year, we talked about that a lot, the capacity to do work, that's energy. All right, and then this is one definitely to memorize for all time. So what is the law of conservation of energy? Put it in your own words if you can. Who wants to go there? Jack again.
It just like it states that energy can't be created or destroyed. It's like if you say threw a bunch of Legos to the ground in a ball and they all broke apart, the energy would be used to push them apart, if that makes sense. I guess or not like you can't just throw something down because it usually, I mean, it might come back up, but like the energy of throwing that down would react and push it back up.
Yeah. So the concept in the law of conservation of energy is that energy cannot be created or destroyed, but it can change form. So a really great example of that was our end of the year project last year for physical science, where we had a lot of energy change in form. And that was a Rube Goldberg machine. If you've never built one, you didn't do my last class, because we built them all over our houses since we got sent home for COVID. We were supposed to build them out in the woods, which probably wouldn't have ticked off anybody's parents, but instead we built them in houses, and it was a little insane. But yeah, you might have like potential energy for an object that's waiting to fall, and then kinetic energy when it is falling. And then of course there's thermal energy and solar energy and all light energy, all many different types of energy. So it can change form from one to the other, but it doesn't ever go away. You know, within a closed system, it's going to stay there and just transfer around, but it doesn't get created or destroyed. So this one was on the homework, and I think some people had a little trouble, at least from the ones I've gotten, a little trouble with the difference. Can anybody explain the difference between temperature and heat? Is your hand still up, Jack, or did you forget to lower? I just didn't know if you were answering again.
Forgot to lower, but I can answer it.
Okay, go for it.
Like he is the energy being. Oh, Abby is answered it, but like
Okay.
heat is just the energy being transferred, and temperature is the measure of the no, I lost
No,
it.
you're close. So yeah, so heat is about energy transfer, right? Heat is about what you feel. It's the energy transfer. But temperature is about kinetic energy, right? It's about how much motion there is within the particles. So when we talk about Kelvin, we're talking about zero particle movement, right? And temperature would be the measure of the movement of all of those particles. So something, for example, like if I put my hand down on my table feels cold. It's really not. It's not any colder than the air around me. It's the same temperature as everything in the room. It's all the same temperature. But what really is happening is what? If I put my warm hand on a cold table, what's really happening there? Cole.
Or I mean, heat. You're transferring heat from one thing to another.
Yes, I'm
It's all just
transferring.
transfers.
Where am I? How is it getting transferred from what to what?
From your body into the table.
Right, because my body's warmer than the table. So my hand, the heat from my hand is getting the temperature of my hand. That heat is getting transferred out of my hand into the table, and that's why it feels so much cooler to me. But it's really not any cooler. But it's interesting, like if you have like a bedroom like mine, I have a hardwood floor in my bedroom and then a tile floor in my bathroom. And if I walk barefoot from my bedroom into my bathroom feels colder. Anybody else have that? Like a tile bathroom and you walk in and you're like, whoo, those tiles are cold. And they're the same temperature as the hardwood floor. But what's the difference between the tile and the wood? Anybody know? Abby's typing. Oh, Alex, you want to go?
How quickly the energy is transferred.
How quickly? Yep. And what's that? What do we call that quality that has to do with transferring heat? What is that?
Quick heat.
Yeah, conductivity. So whether or not something is a conductor or an insulator. So if you're outside, imagine this is 32 degrees Fahrenheit. So 0 degrees Celsius. It's cold for Georgia. You're standing outside in your jacket made of goose down, and you're warm because now your jacket is an insulator, right? So the transfer of heat out of your warm body into the cold air is being slowed down considerably by that wonderful insulator you're wearing. But if somebody put knight's armor on you with no undergarments and sent you outside in a metal suit, how do you suppose you'd feel? Would you feel very warm for very long? No, because that heat's going to get, that heat will transfer right out of your body into that conductive metal, and there you'll be feeling quite cold. All right, so then we talked about within a system. All right, so what's a system? I'll answer that one for you because that's kind of a given, but it's basically, it's all of the components of whatever you're studying, right? So a system can be lots of different things. So endothermic and exothermic. This has to do with whether or not processes absorb or release energy. So some chemical reactions are going to absorb energy, and some chemical reactions are going to release energy. So somebody tell me what's exothermic versus endothermic, and can you think of a reaction or something you experience in your life that might be endothermic or exothermic? Who wants to give it a guess? Anybody? Okay, yeah. Oh, Jack, go for it.
So endothermic absorbs energy and exothermic releases energy.
Yep.
And you want and
Good. Yeah. Mm-hmm. Go
an
ahead.
example is no.
How about you? What are you?
U is a letter. No, I had one. I did. I thought.
So we were talking about my hand being warmer than the table. So Abby's got it. Yeah, humans are exothermic, right? Because we're producing heat. We're releasing heat as part of actually what it is it's the chemical process of aerobic respiration. That's where the heat's getting released. So Alexandra points out when you put your hand on the tile, your hand is exothermic. Yep, because you're exothermic. Just as a human, you're exothermic. So you're going to be all the time releasing heat because the chemical reaction that's going on inside of all your cells at the cellular level. So aerobic respiration is at the cellular level. So we think about a respiration, we think about just breathing in and out. That's just one part of the process. The reaction that's going on at the cellular level is producing heat, and that's why you're producing heat. So have you ever had, like, you bang your knee or something and you go to first aid and they have those little pouches and they go pop and then they shake it and they get instantly cold? You ever had those? Yeah, those like instant ice packs. So that's going to be your opposite, right? That's a chemical reaction right there that is absorbing energy. It gets cold, right? They get cold right away. I swear, when I was teaching at a school, I had kids that would just fake injuries to come get the cold packs because they were fun. Because the more you shake them around, the colder they get for a little while, and they'd just be walking around with them everywhere. All right, so then we got some math issues here. So Celsius and Kelvin temperature scales. Let's see, that's number 6. Those are the two that we're using in chemistry most of all. We use Fahrenheit everywhere else in the world, and we don't use Kelvin very much. It's got to be very few purposes for that one. We're going to use Celsius almost all the time. So what did you get for 7A? Why don't you type your answer in the chat box? And let's see. Anybody? There we go. Yep, that's it. Okay. Now, how did we get it? Did you guys use a calculator, a converter, or did you do the actual calculation online, on paper? It doesn't really matter. I mean, for this purpose, it doesn't really matter. Calculators, yep, yeah. So you can use, we used a conversion factor, probably, if you used a calculator. And it would say something like, so and so many degrees Kelvin equals so and so many degrees Celsius, right? And then you use that factor, which is kind of what we start doing in the lab. We started using conversion factors this week in lab. Okay, and you could also you could ask if you have a spy in your house, the one from Amazon. Yeah, I have her too. Or the one on your phone, you can ask her, either of them, and they know how to do that for you, which is fine. I mean, because if we're being honest, I don't think most people in chemistry labs today are doing the math on with pen and paper anymore, because all this other technology is available. As long as you know how to do it, you're good. All right, so then what'd y'all get for B, C, and D? Why don't you guys type those answers for me? There you go. Okay. Okay. Need to check that one there. I think my book had it. Where's the pen? I misprint the book. All right, there's B. And how about C? There we go. And what'd y'all get for D? Y'all are so good. Super fast. Awesome. Okay. I think most of you guys got it. All right, there we go. So then, hold on. Let's think about number 9 then. Is breaking an egg physical or chemical change? That's an easy one, I think. What do you guys think?
Physical?
Yep, physical. I mean, you're not gonna be able to like stick the egg back together, but you didn't change the substance, right? Substance is the same. How about cooking an egg? Yep, chemical. Abby's got it. So cooking's always chemical. So, you know, so Cole and I were just talking about this today. Cole's a big fan of toast. So when you put the toast in the toaster and it changes color, that's your evidence of your chemical reaction, right? What reaction is that? Does anybody know what that is on toast that causes it to get golden brown instead of just the, the white bread you put in? No, it's carbonization. So that's what happens to sugar. When sugar burns, the carbon comes out, and that's what you're seeing. But you're seeing it in very small amount on your toast, so you get this nice golden brown. But if have you ever burned anything with sugar in it? It's like, it turns like black and gross and nasty, and it smells terrible. And yeah, that's like toasting to the extreme, right? All right, well then how about what happens in terms of transfer of energy oh wait, I'm reading the wrong one there. Yep. What happens in terms of transfer of energy when the heat you hold, I cannot speak today. Energy has heat when you hold a snowball in your hands. So it's just like the table, so what happens with it? There you go. The heat's gonna go from your hand to the snowball, right? Every time. It's always gonna go from the warmer to the colder, because that's just the way it always works. And then here's a good one. So number 12, why is it impossible to have a temperature value below 0 Kelvin? Who wants to answer? Who can raise their hand? And okay, Alex has got it. What you got, Alex?
Because temperature is a measure of how much energy, how much thermal energy something has. And
Uh-huh.
at 0 Kelvin, it has no thermal energy. You can't have a negative energy value.
There you go. What do you guys think? Anybody want to add anything to that, or what? What do you think? Everybody agrees. All motion stops at 0 Kelvin. Yep. There you go. So yeah, if you can't get anything. If you've got kinetic energy, you can't. Yeah, exactly. There you go. All kinetic energy is going to cease at 0. So if it's going to cease at 0, you can't have a value below 0 because there's nothing to measure. It's gone. All right, and if energy is transferred to a substance as heat, will the temperature of the substance always increase? Who wants to give that one a shot? Oh, I think Cole got booted off the internet, but he's coming back now. There are 4 of us streaming in this house. I think it's causing issues.
We're all down.
You're down?
All of us.
I'm not down. My whole family just lost internet, except me. I guess it prioritized.
Know that it's at least working.
I'm fine. Sorry. Oh. So for number 13, that's the number, right? Yep. All right. So your temperature of a substance isn't going to increase if it's undergoing the change, but undergoing a change of state. So during that actual process of changing state is when it's not going to increase. It can increase after it's changed state. So if you've got, if you've got an ice cube, look at it this way, okay? If you've got an ice cube and it's 28 degrees, it's gonna stay in its solid state, right? And as it approaches 32 degrees Fahrenheit, 0 degrees Celsius, it's gonna, let's do it in Celsius. So say you've got your ice cube and it's -5 degrees Celsius. As it approaches 0, the particles are gonna start moving a little faster, right? And its temperature is gonna increase, but when it gets to that point where it's changing state, that actual change of state, there is no temperature change. Then it's gonna keep temperature changing until it gets to switching to its gas state. And then once it has switched, it'll continue to rise. But at the change of state point, it doesn't move, which is kind of a weird concept, but there it is for you. So how about, this was a lot of stuff we went over already, and I just nail it in because I want to make sure everybody understands it. So hypothesis versus a theory. This one's a little different than theory versus law, obviously, which is one of the ones I'm always trying to remind you guys about. So what's the difference between hypothesis and theory? Anybody want to go there? Abby's pointing, she's typing. Oh, she got it. Let her type. I don't want to answer for her if she's got it. Okay.
I'm just gonna unmute.
There, that's easier.
So I figured a hypothesis is a reasonable and testable explanation for observations, whereas a theory is it's already been tested and proven multiple times.
Right. Okay. So that real super close. So with your hypothesis, it's testable. It has to be testable and repeatable and all of those things that we discussed before. The theory is the result of the repeated testing and the hypothesis and revising it and going, oh well, that wasn't quite right, so we'll make a slight adjustment. But remember, the theory is never quite proven because there could always be stuff we don't know. But the hypothesis is your is your good guess, your testable guess, right? And then your theory is the result of lots and lots of testing of that guess and continually getting the same result. So your hypothesis is supported and supported and supported every time it's repeated. That's how you end up at a theory. So we talked about scientific method already, and we had a great little, I think my family's getting knocked off the internet repeatedly. Anyway, we had a nice little graphic, I think, in your first lesson that flowed by this step, and if that step doesn't work, then you move on to this step. But your main ideas for scientific method are that you should be limiting your variables, right? And testing a hypothesis. So when we talked, I think in the first lesson, we talked about, say you had a headache, right? And you did like 15 different things and suddenly you were better. You didn't use any kind of scientific method. So too many variables. You have no way to know whether or not it was the nap or the Tylenol or the cold washcloth or whatever it was you did that made it go away. So that's also something to think about right now, to keep that in mind with all the stuff going on with COVID, because there are multiple studies going on in parallel, and they're all using scientific method because they're respectable studies for the most part. I mean, all the ones that are going to get published, I would hope are done correctly. But there's a big difference between the results they get from those studies and then what we would call anecdotal evidence. Does anybody know what anecdotal evidence is, or how you would define that? So anecdotal evidence is like, it's like saying, well, I did this once and I got the result of X, Y, and Z. So, therefore that must be a correlation because it happened to me. Oh, when I give my dog lollipops, he goes and takes a nap. I mean, that's anecdotal evidence. That's not supported by any kind of structured method for testing or anything like that. And there's a lot of that floating around right now, like a lot of that floating around right now. And then before anything goes from being, so all these studies that are going on right now, they're testing all these various hypotheses. And then what happens is if something is repeatable and supported, then it becomes more of a theory. So the one I read this morning, it was published, I think, 4 days ago, and it was Massachusetts General Hospital System, and it was the largest and most comprehensive pediatric COVID study to date. But saying that, there were 192 kids in the study, which most scientists would say is a small sample, considering how many people are dealing with COVID. 192 is a small sample. But it's a good pilot study to get some information to know kind of where to go. So what they found was that they had kids that they had positive tests for, that they knew had COVID, and their viral shedding levels, basically how many viruses are in them, how much of the virus they had. Their virus load was remarkably higher than that of adults in ICUs. Which means that adults who have symptoms so bad that they're in an ICU didn't have nearly as much of the virus in them as kids who had little to no symptoms, which is interesting because if that is repeatable, if they run that test and get a larger sample and run it and repeat it and run it and repeat it, then they could find out that maybe y'all are just little vectors running around and, and you guys don't get sick, but you spread it. So it's curious, it's interesting. I'm interested to see how it comes out. Nobody should make, major changes of plans based on 192 kids. It's too small of a sample. But it's a good start. They should run with it and see where it goes. All right, so then we talked about that. How about controls? We've talked about controls again many times, but somebody just real quick. What's a control? How would you define it? It's the thing
It's the thing you don't change in an experiment.
There you go. It's the thing you don't change, right? You have what I change, what I observe, and what I keep the same. So yeah, it's the thing you don't change. It's the thing you keep the same. So if you're trying to determine, what fertilizer works best for your plant, you're going to have to keep everything else the same. So the number of hours in the sunlight, what time of day you feed it or water it, how much food and water you give it, all those things, right? Right. All right. And then while we were talking about scientific method, just for number 6, so you guys know, because you guys know it, and this is what we talked about with both 6 and 7. There's no single set of steps, because when you start in science, things can get sidetracked. You can realize that the way you were headed is not going to lead you to any kind of decent results because you started off with the wrong hypothesis or whatever. I see everybody's like, oh, cat. And then obviously for your hypothesis to develop into a theory, it's got to be repeated again and again. So we talked before about no theory being written in stone. We talked about how, look at pretty kitty. We talked before about how science is never settled, right? And that's because, you know, theories explain what's being observed again and again, but they're not a law, right? And even a law, science is never settled. So can a hypothesis that has been rejected be of any value to scientists? What do you think? Can a hypothesis as rejected be of value? So it can be, because sometimes you're going to get something that leads you to change part of your method. And sometimes it just tells you you were, you know, barking up the wrong tree from the beginning. So I don't know if any of you have, well, I know some of you have watched the lab already, but I knew the exact masses of the chemicals in our solution because I put them in the solution. So I had hypothesized roughly a certain ratio at the end. And when I didn't get it, I then had to think, okay, why didn't this work? And it was pretty obvious to me why it didn't work, because there was part of my method that was a little flawed, which I'll show you guys. And then once I figured out what had caused the problem, or I hypothesized what had caused the problem, I have a plan, if I were to repeat this, that would hopefully prevent that issue from occurring again. Let's see. Okay, so how about cause and effect? How does the phrase cause and effect relate to the formation of a good hypothesis? Not just cause and effect, but what's the other set of 2 words I told you guys can very often be used in a hypothesis? Who knows? There were 2 words.
If then.
That's it. If and then. Yeah. If I do this, then that will happen. That's usually a good place to start with writing a hypothesis. Not always going to work, but that's a good place to start. And then control be set up to test the effectiveness. Okay, how would a control group be set up to test the effectiveness of a new drug in treating a disease? So this is a good one. This is done all day, every day. What you got, Alex? Is that your hand?
By not giving them the actual drug, giving them something and saying it's the drug.
Right. So that's a placebo. And there's actually something called placebo effect, which is when somebody thinks they're doing something that is making them better, and it's really not making them better, but it's sort of like their attitude change is really what they feel better, but nothing has been changed medically that should make them better. So that's the concept of placebo effect. And you can actually make it work for lots of things. There's sometimes like little tiny kids, if they're afraid of something or they have a headache even, you could say, oh, you have a headache. Well, this special teddy bear takes away headaches, right? And a little tiny kid might even just take that teddy bear and go, oh, okay. Well, with adults, it's not going to be that. It's going to be, you're in a study, and this is the good thing about medical studies is that they're voluntary, and you get, kind of like reverse psychology. Yeah. You get paid to be in a medical study, but the risk is you might not be getting the medication. So even if it's a study for a new chemotherapy drug, and it's a chemotherapy drug for stage 4 pancreatic cancer or something that's really dangerous that has a really high mortality rate, you may not be getting that drug. You might be getting a placebo, which is just, say they're just putting saline in you instead, saltwater saline, instead of giving you the actual chemotherapy. So they need that data to determine the effectiveness of the drug. But in that process, that means some people don't get treated. And it's awful if you're one of the people that doesn't get treated, but it's the only way people are going to find out if it's effective or not. Does that make sense? Placebos. Sometimes people call them sugar pills, but they're not really sugar pills. I don't know why people ever came up with that one. So suppose you had to test how well 2 types of soap work. Describe your experiment by using terms control and variable. Who wants to give me their idea? Somebody can do it. Somebody can raise their hand and talk. Y'all are all so, like, most of you are gone. I can only see 2 faces. It's like y'all left me today. Oh, wait, there's Jack. Hi. Oh, with the Dr. Pepper. Does anybody want to describe their soap experiment? You can do it. Somebody, anybody? Oh, Michael doesn't have a camera. Yeah, good excuse. Okay, well then I'll just read them when they come in on the homework then, because I've already read. Oh, Abby's typing. Hang on. Abby's a good typer. So yeah, I'll read and see what everybody wrote down, because most of you guys, a lot of you guys have already turned in your homework. Most of it's already in. There you do. Oh, okay. So Shannon doesn't have a camera either. Okay. So models, while Abby's typing, models can be both 3D models, they can be computer imaging graphic models, and sometimes they're just, drawings on paper, but obviously they make it easier to visualize whatever the thing is that's being described to you. It's the whole picture's worth 1,000 words, right? So much easier most of the time. For example, how many of you, raise your hands, have gotten your permit, your driver's permit? Okay, yep.
I have it.
Yeah. How fun was it to try and read some of those traffic laws written down in language?
Kind of confusing.
Yeah, right? Okay, Abby, I'm
It's-
with you. I've been driving for, I don't even know how many years now.
They
And
give you the dumbest situations ever.
yeah, Cole and I were going over his.
I
And
had an app where it gave me a bunch of examples of like things you can and can't do to help like prepare you for the test. And one of them was like, you're going down a street at 45 miles an hour and an old woman begins to cross the street. Do you A, swerve around, B, keep driving, or C, slow down and hit the brakes?
yeah, I mean, one of them actually implied you may run over an elderly woman. But most of them were just, some of them were really, really, really hard to understand. And so we would sit there and he would read it to me, and I would sit there on the carpet in the school with like a marker and a car, and I'd draw the road out on a piece of notebook paper and then like run a little car on it and be like, oh, so it's just so much harder to try and put things like that into words. It's like reading instructions for putting furniture together as opposed to looking at the diagrams. Give me a diagram any day, right? Okay, so we'll do this last bit, and then I want to go over some of the lab with you before I turn you loose on it, because it's definitely a little more challenging than some of the ones we've done before. So this is another one that gave some of you guys trouble on your homework. Accuracy and precision. What's the difference between, oh wait, Abby wrote her soap thing. The soaps are the controls on different types of skin, which are variables. Oh, there you go. Then you would use the information taken to determine which soap works best overall. In short, that's good. Okay, there you go. That's a good one. All right. So accuracy and precision. Who can explain the difference between accuracy and precision? I'll do it this way. Which one is about what's the word I'm looking for? Never mind, I'll do the other one. Which one is about how close it is to the actual value? Oh, Jack's got a hand.
Accuracy is
Yeah, accuracy
the
is
one
about-
that's closest to the true value, and then precision is how close the measurements are to each other.
Yeah, how close they are to each other. There's a word for that I just couldn't come up with. I just couldn't get it out of my head, whatever it was. Yes, exactly. So accuracy is about how close the measurement is to the true value. So obviously the only way to determine the true value of something is to use a very precise tool, right? If you have a tool that is, and it's got to be an accurate tool, but in order to work out how accurate certain measuring tools are, they do repeated measurements, right? Yeah, how similar the measurements are too. Yeah, how similar they are. And that helps them determine the accuracy of various tools, whether it's a triple beam balance or a graduated cylinder. And what's funny is, like, I have a lot of my stuff, a lot of my supplies were purchased at the same time. And then I have other things that I got independently. So I have one triple beam balance that I got from a lady who did exactly like I do. Like, she taught science co-ops for years, and her kids were all gone, and she told some friend, God bless her, she told some friend, when your youngest kid is done with high school, I'll retire. Like, you really like your friend. So she did that for this lady, and then she sold off her stuff at like bargain basement prices. So I drove all the way out to wherever she was, like Stone Mountain or someplace, and loaded up my car with stuff. And then the other things I bought at different times. So we have 4 triple beam balances, and one of them I like way better than the others. It's the one I use in all the filming and everything else. I think it's more accurate. And then I have some graduated cylinders that are 100 mils that are this tall, and some that are this tall. Like, they're different sizes, but the circumference is a little different. So, or the diameter is a little different. But they all come out to the same value because they're coming from a lab that's been careful about it. All right, so scientific notation. This one is about writing very large numbers. It doesn't matter if your number is 0.000000592, or if it's, 453,182,964,483. The whole point is about making the number smaller and easier to read, easier to say, and easier to manage. So we use exponents, right? And basically what we do is you have a certain number of significant digits. One of them is rounded. That's the last one, right? And then you have a times 10 to some exponent. And if a number you're working with is a decimal, it's going to be a negative exponent. And if the number you're working with is not an exponent, a whole number, you're going to have a positive exponent. Now, it's helpful, and we talked about this a little bit, I think last year, maybe the year before, but it's helpful if you work your scientific notation in multiples of 3. And I'm going to show you what I mean. Hold on. Whiteboard. There we go. Because if my number is 3.2 times 10 to the 3rd, okay, what's my number?
$32,000.
32000. Okay, here's why this matters. Where do you put a comma? Right? So if you keep this in 3s, say it's 3.2 times 10 to the 6th, that's another 3. You get 320, 32, 0, 0, 0. There's your zeros, right? It's where the commas go. And it's much easier to read that number, right? So that's why we go there. Ugh. Go away. Oh, go away. Sometimes it's hard to get rid of that guy. Whiteboard. Ah, it shows up and it doesn't like to leave. Hold on. Go. Nope. I told you to go away like 10 times. There. It doesn't like me. All right. So how about let's see, what's a good one to ask you? How about you guys here? Let me see, can I make it do the thing where we divide it up? How do I do that one? No, I don't know how to do that one. I give up. I think I can set this so you guys can write on it. Let me see. Now, how do I make it go? Does anybody know how to do it so I can make you write on it? I haven't done it before. Oh, Lordy. So many options in here. Well, nobody knows. Nobody wants to help me. You're supposed to help me when I get stuck with this. Okay, well, then we'll just come back to it. I'll figure it out. Maybe next week I'll figure it out. I know on our side, click options, click annotate. I think that may be it. Where is it though?
You trying to do?
Yeah, do you know how to do it?
Wait, what is it you're trying to do exactly?
I'm trying to make it so you guys can write on this whiteboard. There's a way to do it.
It's something that we have to do, I'm pretty sure.
No, I
something
think, oh, wait.
it's already allowed.
Annotation for others.
Let me try already.
Hide names of annotators. Oh, there you go. Okay.
I did that.
It was already, I wasn't looking for one turned off. All right, excellent. Okay, so now that we've got that, why don't you guys do this for me?
Just drawing a pee-pee.
Who
Yes,
wants
I'm
to
in first grade.
volunteer to give their answers? We're going to look at 6. Okay. I need A, B, C, and D. So why don't you guys, let's put, somebody can, well, I don't know what that was. Somebody give me, who wants to do A? Who wants to do the answer for A? Whoever wants to do it, raise a hand. Is that you, Jack, or no? Are your hand still up?
Where's A?
Practice problems, 6A.
Do you see it? Okay, Jack, why don't you do 6A?
Come on, Michael.
I can try. I don't know how to write
It's all
though.
right. Give it a shot. Y'all, math scares me too. I get it.
He doesn't understand the mechanics of the writing.
It won't let me.
It won't let you
No,
write?
go up to where it says view options and then hit annotate, and then you can just write, or you can make a text box top of the screen.
Yeah, I should be able to. Let's see. Allow.
See, I go view options. Oh, wait.
Do you see it?
View options. Where is it? Annotate. View options. So it says at the top of the screen you are viewing Danny Start, and it says in green letters.
Yeah, so yours looks different than mine, so I can't see what you have.
So, you know, boom,
Um.
boom.
Oh, there we go. We'll write his name. A, there you go. Michael's writing our A, B, C. I'm missing the D. There's the D. All right. There we go. We're working on it. We'll get better at this as we go.
Yeah, I don't see any options.
Okay. Well, let's see. Whiteboard. Select, save, redo. There's Abby wrote it. There you go. Oh, there we go. Look at this. Here we go. Are you on a computer, Jack, or are you on a phone?
I am on a computer.
Okay, so I'm gonna send you guys some, I'm gonna send you guys some of, there's little tutorials and stuff that go with, there we go, look at this, that go with this stuff. So I'll send you guys some little tutorials and hopefully that can help everybody learn how to use it better. We only had to do it a couple times last year, so I'm still working on it too. But I think it would be good if we all got good at it, because I have a feeling we're all gonna be using it pretty soon, right? All right, there you go. All right. Well, we had an A. Where did A go? Okay. So A was 2.7. Where's my pen? I would rather use my pen. 2.79 meters squared. B was 27. Whoop. Oh, see, this doesn't have an erase. Like, I have to tap the actual eraser. I have a stylus and it has an eraser and it works on everything but Zoom. There you go. To 9 point, okay, will you write for the love of all that's holy? To 9.74 grams per milliliter. And then So, okay, I'm wondering if you guys have this problem reversed. That's odd. So what I have for C is 32.89 grams plus 14.21 grams. And I got 40, so I got this one here. This is what I got for C, 47.10 grams. That's weird. And then I got, for this one, for D, I got 34, this is what I got, 34 point, where'd it go? 09 liters minus 1.230 liters. And the answer I got for that one is 32.86 liters. Do you guys have that? Is this the problem you have for D, or do you have something different?
That's the problem.
Okay, yeah. All right, good then. And what did you guys get for, anybody want, why don't y'all just write it down if you can. What did you get for number 7? Calculate the specific heat of a substance when 63 joules of energy are transferred as heat to an 8-gram sample to raise its temperature from 314 Kelvin to 340 Kelvin. What'd you get? Okay, see. 3.3, good. That's it, Abby. Almost, you got that. There, there you go. That's it, yeah, that's a point. All right, awesome. Okay, and then what else do we still have that we didn't answer for you guys? We didn't answer, okay, I'll write down the rest of these for you, okay? So for number 8, so you can check, okay? For number 8, A, I got 4.42 grams per milliliter. For B, I got, Drew, weren't you in your class? Oh, it's over already, sorry. 24.78 millimeters. For C, I got 1.4 times 10 to the 5th kilojoules per second. That's a J. And then for, that's all I got there. For number 9, I got 5.2 times 10 to the 3rd seconds. And then for number 10, 12 is a count number, okay? I'm just gonna sloppy right there. So if you think about, Michael got booted. If you think about a count number, if you have a number line, all right, and you've got, 0, 1, why am I going this way? Negatives, and then you got your positives. I got to move. You guys are in my way. Where are your faces are in my way? Okay, so you got a 1 and a 2 here, all right? Between 1 and 2, for example, there's an infinite number of numbers, okay? So for number 10, 12 is a count value. So there's this unlimited number of significant figures in here, okay? And then for number 11, it's going to be 3. Density should have 3 significant figures because 9.03 milliliters has only 3 significant figures. Does that make sense? Because if so, I want to look at lab stuff with you before I turn you loose on that. Does anybody have questions about any of this stuff, or are you guys good? I think you're probably good. I think the book does a really good job of explaining everything, and that's good. That's helpful. All right, so this week's lab which is a bummer. We don't get to, let me get rid of this white stupid thing again. And I'm telling you, this whiteboard just, it doesn't like to go away. There it goes. Okay. All right, so for this week's lab, I'm going to put this up here where you can see it. Let me back up a couple slides. I was trying to show this to the younger group, which of course gets super confusing for them. So if you're in a lab group, okay, with any of these younger guys, you should definitely know that I don't expect them to understand all of the math as I expect you to, because they're not there yet. All right, so first things first, in this lab, we're taking 2 salts, okay, and they're in a solution together, and we're gonna end up using fractional crystallization. We're taking advantage of this, okay, the fact that these salts have different solubility for different temperatures. So if you look, this is sodium chloride, and you guys probably know, or a lot of you probably know, that's table salt, okay? So no matter the temperature of the water, whether it's 0 or 100 Celsius, you're still only going to be able to dissolve a certain volume, and it's not going to dissolve more than that. Well, I mean, it's only going to dissolve at a certain temperature. That's what I mean. And then up here, you're going to see that the potassium nitrate, you're going to be able to, it's going to dissolve better at higher temperatures, right? And at lower temperatures, like right here, you should expect it to not dissolve. So then what we see when we get into the lab itself, which you guys are going to watch, and hopefully I made it as clear as I could, we end up figuring out how much salt we have. And just so you know, I'll show you, but this was the sodium chloride at the end, okay? And then this was the potassium nitrate. It's actually kind of cool. Like you can see inside of it in this picture. It made all kinds of neat crystals up the side. It was really fun. It was messy as all heck, which I'll explain in a minute, but it was really fun. So the first thing that you need to know when you're going through the lab, so basically to answer Abby's question at the beginning, the questions I want you to answer are the questions I covered here in the lab. So if it doesn't show up here, don't worry about it. We're good. These are the ones I want. And I'll look back and see if I can figure out if there's a difference between that book and the PDF, because I'm thinking now there is. And usually you find that out after you've started reading it, because there's too much of it to look at the beginning to determine. So we started out by, at the beginning of this lab, we actually get the mass of beakers. And then after we have the solution completely evaporated so that we're left with just the crystals behind, we get the total. So that gives us the mass of the sodium chloride and the potassium nitrate. This part makes sense, right? All right, Jack, got a question already? Yep.
So it says here we're supposed to turn the lab in class. Do we do that next time?
Yeah, next time. Now, if something happens between now and then that shuts us down, what I'll do is I'll swap this over to either a digital upload, or I'll put it in like a quiz where you can just enter your data, if that makes sense. Okay. All right. So this one was a take home, because it takes a while to get through all the calculations and stuff. And we probably would have run out of time in class for all of that. So everybody understands how I got to here, right? We had our mass of our beaker, and then we had the beaker with the salt left behind after we pulled it from the solution. And that ended up giving us the mass of the solution. I mean, the mass of the salt that we started with, of each salt. Now, they were mixed together at the beginning, for those of you who haven't done this. It's a solution that has both of these salts in it, and we take it through a filtration and cooling and heating and cooling and heating, and we're able to separate one salt from the other, which is because we're taking advantage of that solubility characteristic that we just looked at the beginning. So this is where we are when we determine the mass of each one and then the mass of them together. All right, that all is making sense. Here's where we get into the stuff that for some of you might be new. So can I make this any smaller over here? It's in my way. Okay. Trying to make all these, I have all these Zoom windows when you're leading a Zoom, and they're like all over my screen. So I'm going to put this back in. Now I have to move you people. Here we go. All right. So if we go here, it's asking us now, how many grams of potassium nitrate and sodium chloride would be found in 1 liter sample of the solution? So here's what we determined from those initial calculations. We started with 50 milliliters of solution, and we determined that we had 10.3 grams and 7.4 grams. And then what we need to know now is how do we go from 50 milliliters to a liter? Okay, so it's a ratio, right? That's what we're working with. So I'm going to show you 2 different ways. The first way is if you consider that 1 liter is 1,000 milliliters, right? So how do you get, if we want to get to a liter, how do we get from 50 milliliters to 1,000 milliliters? How many times does 50 go into 1,000? Who can tell me that one? That's an easy one. So it's 1,000 divided by 50 is what? Somebody popping up. Oh, God, 20. Yes. Okay. So it's 20. So once we know that, 50 goes into 1,000 20 times. So you can set it up like a fraction, and this is your conversion factor. So it's just like the reverse of reducing the fraction, kind of. So if you look at it this way, to get from, here's your fraction here, because it's 10.3 per 50. Per means fraction, divided by 10.3 grams per 50 milliliters. And you want to get to 1,000 milliliters. Well, you do that by multiplying the bottom by 20 and the top by 20. And when you do that, you get 206 grams of sodium chloride per liter. You do the same thing down here, 7.4 over 50, 20 on both, and then you get 148 grams of potassium nitrate per liter. That makes sense, right? Does that look familiar, like something you've done with fractions before? Does that look like anything y'all have done before? Okay, all right. So then, ooh, I did not mean to make that. Okay, good. Go away. This is maybe something you've not done before, but this is more how it's done with chemistry and engineering, and that's using a more traditional conversion factor. So we're going to look at this in a different way. So you've got same thing we started with, 10.3 grams per 50 milliliters, 7.4 grams per 50 milliliters. So there's a fraction again. All right, now what we need to look at is if we look at milliliters and grams, we're trying to get to how many grams per liter, right? That's what we want to know. So we need to take, here's what I have, and you have to determine what you want to keep and what you want to get rid of. So if we're trying to get from grams to milliliter, which of these 2 units do we want to keep? Does anybody know?
Milliliter.
We're trying to get from grams to liter. So if we're going to go from
Liter, sorry, liter.
well, so yeah, but we don't have liter. So that's the point we're getting to. Yep, you're right. You're right. So we want to get to liter, but we want to keep grams, right? Okay, so if we want to get to liter, then we have to get rid of what? Yep, Abby's right. There are 1,000 milliliters per liter. If we want to get to liter, we have to get rid of milliliters. We don't want it. So what we need is something we can multiply by that's equivalent to 1, because on the other side, when we just looked at the one before, what was equivalent to 1? It was the 20 over 20, right? We basically multiplied it by 20 over 20, which is 1, right? So what's equivalent to 1 that'll help us get rid of milliliters? Well, in this case, there it is. 1,000 milliliters is equal to a liter, right? So this, does everybody agree with me that this is 1? It's the same thing as 1. Okay, the same thing as 20 over 20, which is what we did before, okay? So if you've got 1, oop, I have a chat. Oh no, okay, it's just a yes. All right, so if you've got 1 and we've got milliliters here and milliliters here, well, in a fraction, you guys who've done fractions in math know that if you've got the same thing on the top and the bottom, you can get rid of them, right? So this is our conversion factor, whereas before it was the 20 and 20 over 20. This time it's 1,000 milliliters over a liter. Well, the beauty of this is now you can just simply get rid of the milliliters because they cancel each other out on top and bottom. So then you're just going to multiply it straight across. It's that easy. And that's what you get when you multiply straight across. Well, now you're going to take this 50 liters and 10,300 grams for 50 liters and just do the division and, you know, divide 50 into 10,030 and you get 206 grams per liter, which, do you guys agree that's the same thing we got before? Okay, good. So do it again here. Same thing, it's exact same thing, right? Because we're the same one, because we're still trying to get to grams per liter. When you multiply across, there you go. That's the same thing we got before too, right? Okay, so now if you guys agree with that, then we're gonna look down here because it happens again. It happens on this one. All right, so for this one here, this is when it starts to get really complicated, and it'll make sense when you've worked your way through the whole lab, but I wanna make sure I've shown it to you before. So it says here, the company that you work for, this whole lab's about this company hiring you to determine what's in this solution that got mislabeled. So they have 55 liters of the salt mixture dissolved in water, just like the one you worked with. Now you guys worked with 50 milliliters, right? They have 55 liters now, but they want to know about. And they want to know now how many kilograms of each compound, so the two salts, is in this big 50 milliliter sample. Okay, 55 milliliter sample, sorry. So what you need to do here is we can do it this way. This is the fraction way. And I'm showing this one to you because it's more familiar, but we're gonna try to use the other one as much as possible. So you can ask yourself, you know, how many times does 1 liter go into 55 liters? 55 times. All right, so here we go again. We have our 206 grams of sodium chloride per 1 liter. Our one will be what? 55 over 55. So there it is. And there you get 206 times 55 is 11,330 grams. Okay, how many kilograms? There you go. And that you can do by scooching your decimal or dividing, however you want to do it. Does this way look familiar to you? At least makes sense, as in something you've done with fractions before. You get the idea. Little bit. Jack's like, no way. Okay. Well, I'm showing you because it may look more familiar than the other one. So yep, there you go again. Multiply 55 by 55 all the way across. Okay, but this is the way we're going to do it most of the time. So here we are again back at conversion factor, traditional conversion factor. So we had 206 grams per liter, and we want to know how many kilograms per 55 liters, right? So we have to get rid of both grams, and the liters can stay. We want 55 liters, but the grams we need to get rid of, they need to become kilograms. All right, you got that so far? Everybody's got that so far? We want to know how many kilograms are in 55 liters. Jack's leaving the screen. That's excellent. Okay, now it's not too bad. All right, so what are we going to do? We want to get rid of the grams. So the first thing we're going to do is come up with a conversion factor that equals 1. I'm with you. That equals 1. Okay, so this is, y'all agree this is 1? A kilogram is 1,000 grams. Okay, there's 1, and it allows us to get rid of the grams, which is what we're trying to get rid of, because we want kilograms per liter, but we don't want 1 liter. How many liters do we want? Who knows? Who remembered? How many liters do we want? 55. So 55. So here we go. We work our way across, and those go away. Multiply straight across. Do your division. And there is your 11.33 kilograms per liter. And then if you do the same thing here, boom, there you go again, and there you go. So this is what we had for a kilogram per liter, right? And if you're going to multiply it by 55, that's what they're going to get. Okay, so we're actually gonna, I think, let me get rid of this. Go away. It's in your lab, and it should be, it's in there with me explaining it as best I can. I don't love math. I love science, but I'm one of those people that loves the science, and the math's like, but it's okay. So does anybody have any questions about the lesson? We're good for the lesson? Okay. And then for the lab, just work your way through it. Watch the video, keep your binder out, fill in as you go, okay? If you catch a mistake, let me know. A couple people caught mistakes this week, so you guys gained some extra brownie points. That's all good. And then anything that comes up between now and next week, let me know. But otherwise, are you good? Yes? No, Jack's not good. Did you see the video? I'm gonna find some other videos too. When I do my weekly updates, the email's probably gonna come a little late because I have to run my coughing person for a test today. That's fun. And so I'll send, so I can send that video out. I will send that, that email out a little later than usual. So that being the case, I'll find some good videos to put in it for you guys that should have extra explanations, different people explaining different ways to look at it. So hopefully one of them will be the one that clicks. Anybody have anything before we go?
I have a question.
Yes.
Or it's not really a question, more of a state. Like, speaking of like videos and like, I'm really bad at math. Like,
Yeah, me too.
really, really terribly bad. And I found this guy on YouTube who's really been like helping me like get through like the conversion factors and stuff. So
Good.
I'll probably be like leaving it in my Teams forum if anyone wants to like come like get his
Absolutely.
link. So if anyone needs help with the math.
Great. No, thank you. I appreciate that. Actually, Jason came in here and ran through some stuff with me the other day too, just to refresh. He can remember like he's got a very math brain. He's an engineer. So everything he's ever done with numbers, he remembers and he's like, oh, but I need refreshers at times. And I have a documented disability with math. It's like dyslexia, but with numbers. So it's real fun to get a degree in science with that. Let me tell you, it's a lot of work. So yeah, all right, I'm gonna let y'all go then if you're good, and just take your time to go through the lab. I extended the homework hand in till 8 p.m. so you have time if you didn't already hand it in. And questions? Anybody? Anything? Are we good? All right, I'm gonna let y'all go then. Hopefully I'll see you in person next week. Okay, bye.